Thank you very much for inviting me here. So, a great introduction to the company. So, we work mostly with managed connectivity, meaning that our customers connect their devices, and these devices can transfer data to and forth the internet or their home network wherever they are in the world. So we have like a roaming partner agreement. So these cars, devices, things can move across continents, countries, mobile networks, and they're always connected. And this opens up a lot of cool use cases and so on. So just to give you a flavor, I won't stay so much long in a company presentation, but this is a familiar car model. Volvo Car decided last year to connect every single car that leaves their factory. Okay, one of the killer use cases are the Volvo on Call, where Nordic car owners of this brand, they can sort of program when they're going to leave in the morning, and the car will be done. Sort of no ice, it will be home warm, and the same when they go home. That is a killer use case that drives adoption and drives data, Internet of Things data. So, but they are all connected. And other examples are home alarms, very short, for instance. Interestingly here, you can protect your alarm. Once it was a copper cable that the burglars cut, and they put a SIM card into the central unit, and they get rid of that issue. And once they could send data, they found an app so you can control your home alarm, and my kids are back home from school. That's what I'm going to tell my neighbor, and they're going to buy the same. So there's sort of a lot of things that triggers sensors, the use of sensors and use cases in Internet of Things. Other cases are Scania trucks. So for instance, they are providing not only the trucks, but also values on top of this, because all these machines and vehicles are connected, so they can measure oil pressure and so on. I think we have people here from Scania actually, and they can sell service contracts on top of their product. So add value-added service, so guarantee uptime more or less, because they can measure everything all the time. Other examples are Volvo trucks and buses, of course, and then there's a sign saying how many minutes the bus before the bus arrives. So the GPS receiver in the bus, and then that needs to transfer that data. It's not just satellites that communicate; it's data, the geoposition. But the cooler use case is actually back in my hometown, Eskilstuna. I asked one of the bus drivers, one of these buses, and they had a display there besides we were driving with 2 bars going up, red and green and so on. And so I asked, what is it? Yeah, well, we are measured by eco driving. So as a bus driver, I get 300 euros every month in a bonus if I meet the full percentage of the eco driving. Okay, so a huge cost of driving buses is fuel. And if you can keep your timetable and drive eco, less fuel, there's incentive, and the ones that has the power to do this is actually the bus driver. So this is not a cool use case. So there's lots of them. So let's go into some, what I'm really going to talk about. Mastering real-time data analytics. And most of us data scientists never had the luxury of work with real-time data in history. We worked with something called batch, data sets that were controlled, sampled, and so on. So how do I take on this subject without giving all our trade secrets? Okay? I'm proud of what we've done, and it's really cool, but what can I tell? So I've lifted this up on a slightly higher level, but not as high as, corporate bullshitting, I hope. So it will be like a successful design principles, but from a data science eyes and perspectives. So I have a friend, a colleague back at Telenor Connection that is also giving lots of lectures and speeches. And he formulated elegantly a formula for how making money out of data. And it's no news. It's will you be like, yeah. But it contains, of course, data. And you need to process and enrich something. And you have analytics, which to gain you insight. And then you need to take action. And if you add all this together, There's money down your pocket. Cool. So the more real-time the data is, the faster you can process and enrich it, and thus you can also know what the data means. You can analyze it and derive insights. And not a few, but rather a bunch of companies sort of stop there. They are happy with insights, but it's actually like this. It's important to know that only the insights that are actionable are the ones that actually will have an impact on your business, or considerable impact at least. So have that in mind. You need to think about action. I think the former speaker in this room touched upon many of these topics. So some of it will be iterated or articulated. But let's go back a few steps. So most of the data must be processed and enriched. So when it comes in byte encoded or without any sort of external data, without any, you don't know what data points come from which customer and so on. So you need to enrich it somehow. And that you typically need to do before. If you work with batch data, it's simple. You can, but you need to do this at least before you analyze. And if you work with real-time data, you need to do this before you analyze your data. We all once lived in a world of batch jobs, nightly batch jobs, for instance. But fortunately for us data scientists now, or your data-savvy decision makers out there, there are now super cool, highly stable, super scalable technologies. And most of them are spelling cloud or smells big data. But in hindsight, I mean, we have been a production load of real-time big data platform for several years now, and very successful in that. In hindsight, this might be like, oh, a lot of new technology, and we don't have the skills. But this was actually very simple and very fun. So don't be afraid of this. So, well, working with batch data, one of the most convenient aspects is that you can fix all your reference data afterwards. You can collect your data, and then when time of analysis or processing, you can add your reference data. Go and ask the guys that knows what the data means, add that, and it will all work. But in real-time data, it's sort of different. You need to do this before. But it actually gets worse. In reality, the reference data is also constantly changing. And you need to maintain it and update it. And hence, working with real-time data, you need also to think of this and continuously updating also the reference data, not just having a streaming data source. So if not in real time, but possibly maybe you need to sync the reference data at least daily or weekly or monthly. And the solution to this is either hire a bunch of data monglers to do the trick for you, or you automate as much as possible of this. And the obvious, of course, is that automation is preferred. And it's not that proud, but if you look at what we've done with the reference data, it is like there are CSVs, there are spreadsheets, there are SAP reports, SFTPs, APIs, web services, database connections using SQL and connection objects, there are homebrew details, there are even business rules encoded in the algorithm, so to say. So how the hell does that work? But this is what data scientists need to do on a daily basis, more or less. There's always never good data in place. So, but the thing is that what we learned is that as long as you don't integrate with a human, it all works out very well. So as long as there's systems that produce these or have these interfaces, sort of spreadsheets, if they're not produced by a human, by a machine, they actually works as a data transport format and so on. So that's, so humans are nice indeed though, but they are not consistent. They are not as consistent as machines. So should you do all your automation at once? Likely not. You should start with a good baseline and then add step by step where it adds value, or adds most value. So now when we can understand the data in real time, what are the next important things to sort out? Typically, real-time data means big data. I typically describe it as if you get real-time data, you get big data as a consequence, not the other way around. You shouldn't start with big data and then go into real-time, because you missed a lot of critical design steps there. Nevertheless, no person, department, organization will be able to look at all the data points and go through that day after day, or even so, less so do that in real time. So the smart way, of course, obviously, is that you narrow your search space using machine learning and to try to extract those events that you should actually act on, okay? And let's call them deviations from normal. If everything is normal, you don't need to do that much. If you don't want to do like a strategic move of your business models and so on. But daily operational, normal is good. So the standard procedure looks like something like this if you're going to detect something. You collect as many examples of deviations as possible, or as you can come across, and then you add some normal data to that, and you train a machine to distinguish the two apart. An important thing here is that, well, the number of deviations here that you're using the training model is sort of proportional to the power of your predictive machinery. And this given that you haven't enough data to train on, that you saturated the model, so there's nothing more for the machine learning algorithms to learn. But we are seldom in that case. We have actually have a different situation. But what if, like this, all the deviations look different all the time? Meaning that the training data is not representative of the data it will be later fed on. So, well, all those binary classifications or regression algorithms will they will fail big time. So how do you teach a machine to learn the unknown? Well, the solution, as we at least attack the problem, we sort of model the normal, okay? Because that is well defined. That's the same. We have data for that, and we know what it means. So, and then we somehow measured every new event that was a deviation, like a distance from the normal. Okay, so that's a way to. So if you have a distance metric from your expected distribution, that is a slightly more effective way than modeling something that will always change and that you cannot rely on. So by becoming a master of what you actually already should know, the normal business, you can more easily spot those deviations that are worth acting on. Cool. Now we found a new way to detect only the things that will require our attention or even actions. We just rely on the fact that we can describe and model that what is normal. But now, well, there are more headaches. Even what is normal is changing over and updating over time. And what is causing this change can be a number of things, but in reality, it can actually be a very good predictive model. And the lifecycle models is something like this. If you develop your model, implement it in your business, it actually impacts it. The better the model is, the more it will impact, the faster it will push your company or your organization into a new normal, which is better and different. On the other hand, your model will be outdated. So there's a life cycle perspective of all models. And the best ones are the ones that live shortest. However, most companies, well, this drift or change of state over time is not at the speed that you cannot do a remodeling and implement a new model. Typically, businesses and organizations change very slowly. But that's not all the case for everyone. digital upcomers like Spotify, King, and all those, and also us. We are fortunate companies that act in an area of extreme growth. And like us, for our sake, sort of, we face that our normal is actually changing all the time, and in the rate of an exploding market. So what is normal for us is so it's changing, and we'll have millions of devices across the world, and each of these devices probably impacted by hundreds different external parameters that we don't have any control over. And we just need to embrace the fact, warning, the only thing that is constant is change. You heard it all before, and you can say, yeah, that's a good statement. Yeah, we need to transform our business and so on. But we not only took it to our hearts in our organization and live by this, we implemented in our data pipelines and our analytical engines. Only thing that is constant is change. And if you have that mindset when developing all your architecture, your systems and your prediction models and how you're going to act and steer, I think you're better equipped and will have successful long-lived systems rather than doing some requirements-based, this is what we're going to solve, and then implement it. So what is driving change for our end? Well, the most obvious parameters is that an addition of new customers, but also customers that they deploy more devices over time. And the local markets, we are in a global player, so the local markets can gain adoption. Suddenly, everyone wants to buy a connected refrigerator in Germany. I don't know. There are also customers that they have their own product lifecycle. They have different models that they connect. And when they launch a new model, that model has a different connectivity pattern and affects all our network congestion and so on in a different way. So all these things, and we don't control that. That is what our customers are doing. But we need to make sure that we can deliver good services to them. So these are even world economy will impact us in our models, of course. And I don't think that we are alone in this. So how do you treat this? How do you solve or attack or manage it? Well, the obvious way, not surprisingly for someone that looked at or in data science and so on, you sort of compensate for a drift over time by using a sliding window. So at every given time point, you look some period back, let that be normal, and then you say, what does this last past weeks, months, years, or whatever, how does that sort of predict about what happens today or tomorrow? And the good thing with that approach is that will sort of follow your data where normal. But it's also important to make sure that you also compensate for those natural variations and the periodic patterns, such as day or week, or time of day to customers or users maybe, but also geolocation. Because those are not important to predict. They are actually part of the normal. So you need to sort of have that dimensions in your models. So once you have all of this in place, our models now are automatically calibrating and self-tuning, so both regarding internal and external data. So very nice. So we don't do any remodeling. It's just a data-driven, new data filled into the model, same models, and each model has its own sort of dependencies there. So let's then look at the final component, which is action. And I won't talk long about how to automate actions and so on. I'll give the data science part of taking action, which is not only to say that what you should act on or when, it's also about how accurate or precise you can estimate that the model will be when applied in reality. So here's a fictive example. A data scientist is given some data and builds a model that finds 98% of all abnormals, with only 1% false positives. This may seem impressive at first, but how many are data scientists here? Quite a few.
A lot more now than in the morning, actually.
Yeah, they are morning tired or all sitting up all night and crunching data. I don't know. So I mean, well, have you ever had like a model like this? Probably not. Only a small fraction of data scientists would be proud of this model, because they would rather be suspicious and worried. Have I included some dependent variable in my predictor here, just which isn't there in reality, or have I just made something really wrong in my algorithms? In principle, data scientists are not called in for these simple problems. But let's, for the sake of it, for the sake of an argument, stay with this model and assume it is correct, and have a look at what happens in reality, even that we have an almost perfect model. So in this example, in reality, we have a skew distribution, 1 to 10,000. So an abnormal event happens very seldom, only 1 in 10,000 cases. And that will lead that, although we had a really low false positive rate, there will be 100 false positives for every right alarm, which means that you're sort of cry wolf all the time, and putting such a model in place in your data pipeline is probably not a good call. There are ways to improve your stats. You have your Bonferroni correction or false discovery rate methods and so on, but they all have their trade-offs and so on. But you might probably need to pick some method to correct for this, the one that suits you best on your use case. But a final remark on real-time predictions is that you can actually have some compensation for that. Because if you trigger an alarm and it goes back, maybe it's back to normal again. You didn't need to act. You didn't have time to act. But if you sample over some time and the alarm is persistent, then it's more likely that the alarm is triggered not by noise or an oversensitive model. It's actually a real signal. So that's one way, but this is most algorithms, prediction models have this problem, and you need to think about this in terms of taking actions. What are you comfortable in actually implementing in your operational aspects? So my take-home message then around real-time analytics. It is great fun to work with, and there's some awesome technologies in place. This is really cool to work with real-time data. It just streams magic. Data is magic. So if you get your guiding principles on what is important for your business right, then there are talents out there that can help you implement this, or at least pick up what's needed to learn. But you need to have your guiding principles of what is important. How often am I able to act? What is the data I need to make intelligent decisions? When do I need it? What is the latency I tolerate, and so on? And most companies does not need millisecond latency. Humans typically need to make a call. And the speed you dial, even if you have a speed dialer, there you need some courtesy phrases you need to do. So there's more time you have in most cases than just milliseconds. So regarding reference data then, yes, it's about a lot of hard work or automation. I think that's, or maybe I simplified it, but that's really critical. Have your reference data in place if you work with real time. You don't have the time to wait till later. Then the value of real time is just gone. And my advice, if you work with real-time data analytics and predictive modeling, focus on what is normal and look for the deviations, and be extremely cautious about extreme skewness in the data, the actual data, I would say. So, thank you very much. It's been a pleasure, and hopefully there was some things worth coming here for today. Maybe it was new insight or articulation of what something you already knew, or with just, yeah, good food. Thank you very much.
Thank you, Anders. A big hand for Anders.